So now we should be recording. Okay, so on the website, under lab materials, you can grab the data set we're going to work with today. It's called route.jmp. And this is sort of an idealized data set of one that I actually have, which is different routes I take to campus and the times it takes for each. So go ahead and grab that. And this is something I know it's silly to do, but so when I moved to my new place, I was really concerned with what the most optimal way to get to campus was, and there was lots of different routes. And these are some that I was considering. So let me just orient you to the data set. We have 4 different routes that presumably when I did this, I randomly selected each morning. So going Nobel, going Gilman Drive, Ohio Village Drive, or Genesee, so to get actually to the psych building. In this data set, I have just 3 different times a day. In the actual version, I just recorded the actual time, but we're going to treat this as just separate groups now. So 8 o'clock, 8:30, or 9 o'clock. These are times I was leaving my house. And what we're looking at is times in seconds. This average is a lot faster than it normally takes me, but for these data, you can sort of see what we're looking at here is roughly around 10 minutes for all these different routes. So the question is, if we set up this experiment in this way, where over 40 days, and let's pretend I'm actually randomizing this in a really good way so that every morning I randomly determine, let's say by a coin toss or some sort of process, what time I'm going to leave, and I also randomly determine which route I'm going to take. So if I do that and do this randomization correctly, then these data actually will let me determine which route is in actuality faster, right? But of course, with all things, there's variance in nature, right? Traffic conditions, other conditions that may affect the time that aren't within this manipulation. So for example, traffic may just be especially bad in certain routes at certain times of day, but not others. So treating this as a factorial experiment, which is essentially what we're doing, right? We're crossing factors. Every route has instances at different times. By crossing this, we're going to be able to get a couple things out of the analysis. One, an effective time. Is there a time of day effect? Is it actually faster for me to get to campus earlier in the day than later in the day? A route effect. Is there a difference in the routes, right? Is one route faster overall than another? But also the interaction, right? Is there something special about a certain route at a certain time of day, right? Or is there no interaction? Is it that every route is uniformly faster a certain time of day than another, right? So by collecting data in these ways, we're going to be able to answer those questions empirically. And the nice thing about this is, of course, if you just were to take each route one time, you would have no way of knowing whether it's actually a route difference or a time difference or something to do with the variability there. Or, you could have gotten lucky. I could have chosen a day that happened to be really quick to take Gilman and really slow to take Genesee. So of course, with all things in nature, we have to take multiple observations. That's why we do statistics, right? To see if we have evidence that truly in the population, and in the population here is really truly in reality for that route, is there a time difference? Okay, so the first thing that I would do if I just collected these data would be to get descriptive statistics, right? To sort of explore the data set a little. And the way that we did that with regression was, of course, looking at just the distributions of each of our variables, which is just helpful to get oriented to your data. So let's just do that. The day effect here, or the day, is just a count variable for each day, so we don't have to really look at that. Hopefully, we just have one data point per day. So let's take actually time, route, and time in seconds, and stick those in our y. And what we get at is the single variable distributions for each. So we can see that we had almost the same number of observations for each time. 8 o'clock got 1 extra observation, only because 40 is not divisible by 3. So one of them had an extra one. The route, if I were to actually do this randomly, I probably wouldn't get perfectly equal numbers, but let's just pretend I did. So each route to campus got 10 observations, so 10 different days. And if you look at our distribution of time, you can see that it's roughly normal. There's nothing terribly non-normal. We have one point out here that's a little bit beyond the distribution, and if we have some time, we'll talk about what we might do with that. If I were to see this, I wouldn't think that's so horrendously beyond the distribution that I would do anything with it probably. But of course, if we get results and we're trying to see if they generalize, we might want to consider taking that out, running the analysis again, and seeing if our inferences hold. So at this point, we have really all the information we can get out of just the single distribution plot. But we have 2 qualitative variables that we're crossing, right, in a factorial way. So we might want to know whether we have equivalent numbers of observations at 8 o'clock for each of our different routes. And so one way we can do this quickly, if you don't want to rerun a different analysis, is just selecting that 8 o'clock bin. And you can see roughly across the range of routes, we have observations that are about equal in number. We could do it for 830, and you can see the distribution there, and for 9. What's great about JMP, though, is its ability to really graph information. And one of the things it does, which I think is really cool, is mosaic plots. So mosaic plots are a type of way to model or to graph nominal data against nominal data. So to show you what that looks like, let's go back to Analyze. But this time do fit y by x. This is going to be a way of fitting one variable against another. What we're going to do is actually take our two nominal factors here, time and route, and we're going to put one as the x factor. I'll just choose route in this case. And I'm going to stick time as the y. And notice that both of these are nominal, right? They're categories. And so it's saying down here that this is going to be a contingency analysis, right? So if we wanted to do a chi-square type analysis on this is how we'd set it up. Here we're just graphing them to make sure we have equivalent numbers or so in each group. And what it's going to produce for us is this mosaic plot, which is a really neat way of graphing nominal data. I'm just going to drag this out to make it bigger. And what it does is graphically show in terms of proportion of area just how many or how frequent each observations are. So the most frequent, for example, for the Genesee route, the most frequent time of day was actually 8 o'clock, right? So it outnumbered the 8:30s and the 9s. But you can see that this distribution, so this proportionality here is not the same for every route, right? So it differs a little bit. And this might happen if we're actually randomizing our orders of time of day or the routes we take. You might get something like this. Now I bring this up because if you're doing analyses with sort of randomized factors like this, you really have to be concerned that in one condition you don't have very few or no observations for a certain condition. So imagine if I had done this over 40 days and I actually never took Gilman Drive at 8 a.m. So if I never took Gilman Drive at 8 a.m., it's going to be presumably hard for my analysis to deal with that or to predict what that mean should be. Right? So you have to make sure that you have roughly equivalent numbers of observations. Equal n is not a necessity for analysis of variance the way we compute it now. We have ways and strategies of handling that computationally. But one thing the analysis can't deal with is missing cells. Of course, you can impute data. You can make up what the data should have been for that. That's not a great solution. So I would say, always make sure you have enough observations in each cell where it's not hugely disproportional. And Mark mentioned this before, that equal n is not really necessarily the smartest thing to do. If you have groups with huge variances, you might want to actually have more observations there, so your estimates of those means are equivalently precise. We'll talk about that later on. For now, we're just making sure that we have an estimatable function for our actual model. We need observations in all cells, so we know what those means are. Just as something I could point out down here at the very bottom, it's producing tests for us. These tests are, well, they're not useful for us now. They're also sort of nonsense, especially because if we randomly picked these groups, if we randomly decided what time of day to leave and what route to take, then any chi-square test that's telling us whether the proportions are different, greater than chance, it doesn't really tell us anything because we know chance was the only thing that was determining who got in each group, right? Just so you can see it, our p-value here, our probability greater than chi-square, that's like a test statistic to say, are the proportions different across the groups? So if you were doing a chi-square test or wanted to test proportions, this is actually the method you do it in JMP, but for us, this is actually meaningless. We don't care. Okay. So now that we sort of know what our data are and what we're dealing with, we can start actually performing analyses. So we're going to start, though, with a one-way. So we're only going to consider one of the factors at a time. We're going to eventually get to consider both of the factors, but to start, let's just think about one. And route's probably the most interesting one for us, or was for me at least. What route I should take to campus. Time of day is something that, well, it depends when I wake up, so it's not something I have as much control over, I guess. But route is, one that I can decide when I get in my car. So let's look at first using fit y by x, which is a totally fine way to do this analysis, but you'll see that fit model is going to be a lot more flexible, just like it was in regression. So open fit y by x. And our factor here is, as you might expect, route, right? That's the factor that we're trying to get a handle on what effect it has on our dependent measure. So put route in the factor, and we're going to take time in seconds and have that as our y. And notice that it's going to tell us it's going to perform a one-way analysis here. This is just the analysis that it's going to do if we have a nominal factor and a continuous dependent measure. So I'll go ahead and hit OK. And to start, it's not going to do anything for us except for plot the actual data points by each group. So you can sort of visually see what the spread of the data are for each group, and they're roughly equivalent, which is an assumption of the model once we actually get to fitting an analysis of variance. But for now, this isn't producing for us any real analyses, right? It's just plotting the information. So to get the ANOVA, what we're actually trying to produce here, go to the little drop-down menu, and it's just right there. It's means and ANOVA. And what that's going to produce for us is the standard one-way analysis of variance, looking to see if it's sensible for us to think that all these routes are equivalent in their time to campus. That is, are they the same duration in the populations? It's using, of course, our sample data to make that inference. And so when we run this, you're going to get something that looks a lot like your regression output. It looks very similar to what we were getting before. It has a summary of fit with an R squared, so a proportion of variance that all of our factor can account for. Our root mean squared error, our best guess of the population standard deviation, our number of observations, the average of the y's, stuff like that. But the most important thing for us is going to be this analysis of variance table, right, which is actually the root or the seat of our analyses here. So as Mark mentioned, ANOVA tables used to be more popular to be published. They're not really anymore, but they're definitely good to get in the habit of reading. Really, all programs produce something that looks like this. They have some source, and they list it differently for each program. But they'll list a source, a degrees of freedom, usually your sums of squares and your mean square, then eventually some F ratio and a p-value. Again, this is our omnibus test. So this is our test of whether all the means are equal or whether one mean is different as the alternative, or at least one mean is different. And our sources here, we have route, which is essentially our effect of the between subject factor we have, right? Our effect of the different ways I went to campus. Our source for error, so this is our pooled within cell error. After accounting for mean differences, this is the residual, or the amount that people are still differing from their group means. And then we have this corrected total, just like we did in regression. This is just the sums of squares for the y variable. And if we look at our p-value here, we see that it's substantially less than, presumably, our alpha of 0.05, which is telling us that, yes, we have some evidence that one mean is different at least, right? So something is happening here. We have some reason to think that these means are not all equivalent in the population, or not all routes are equal. But as I said before, this isn't really localizing any effect for us. It's not telling us which group is different from which other group, which probably you can sort of get a handle on if you look at the means. You can see that La Jolla Village Drive, for whatever reason, is taking longer on average. And you can get at that if you look at the means down here. But really, at this point, all we have is evidence that something is happening, that some group is different from some other group. But we haven't yet sort of specified which one is different from which other ones. Okay, so before I do the same analysis and fit model, is that pretty clear how to run this in here? Now, one thing I'll note is, just like I've said before, JMP is very sensitive to how you code your variables. So make sure that you have, if you're using a nominal factor, make sure it is scaled as nominal. Otherwise, JMP is going to try to run a regression. So actually, none of my variables here could possibly be continuous because they don't have any numeric quantities. But sometimes, you'll have a factor where you have the levels coded as 1, 2, 3, 4, 5. And it's really easy to have that marked as continuous. And what it's going to try to do is regress your dependent measure onto that 1, 2, 3, 4, 5. And that's going to do a very different analysis and give you pretty much nonsense results, almost certainly. So make sure if you have a nominal factor, of course, make sure it's marked as nominal. Okay, so let's keep that open. But let's do the same analysis, this time using fit model. Just going to analyze fit model. We're again just going to use route as our factor. So I'm going to add that into our model effects section down here. And again, we're going to take time in seconds as our y. And you'll notice that our personality doesn't differ at all from what we had in regression, still using a standard least squares. And in fact, we still have the same options for emphasis. I'm going to leave it on leverage. But of course, this is just determining sort of what output is produced by default. You could always request additional output if you need it. But I'll just leave it on effect leverage for now. So go ahead and run that. You notice you get a little bit of extra stuff. You get this actual by predicted plot, and you get that leverage plot for the factor. I'm just going to actually minimize those so I get this up higher. Excellent. We get the same summary of fit table, and all these numbers are going to agree. But the one thing you actually get beyond this actually before we get to parameter estimates, notice that effect tests is an extra section here. That is listing just our factor. So our factor, which is route here, is listed under effect tests, and we get the same p-value we got before. Now if we had multiple factors in there, we'd be able to find the effect of each factor under that effect test section. And that's really important to remember. It's under effect tests and not under parameter estimates. So by default, it's going to close this little tab for us. But if you open this, you'll notice that you're going to get a lot of extra tests and p-values. And it can get sort of confusing, especially if you have lots of different factors. Just remember, if you're looking for your effect of a factor, it's always under effect tests, not under parameter estimates. Parameter estimates is something completely different, these tests that it's actually running here. And we'll come back to that at some point, probably after I talk about pairwise comparisons, because that gets a little bit complicated. But for now, remember that this is not where you're looking for the effect of your factor. That's under effect tests. Let me actually close that. One other thing I'll note about this fit least squares is that by default it's going to produce this residual by predicted. Now, this is sort of what it was in the regression, except now it's putting them into different groups instead of scaling it across a quantitative variable. So remember, our residual by predicted is just literally your residual, so the amount that each person is differing from what the average of that group was. So an analysis of variance or residual is just how much you differ from your group mean. And that's all it's plotting down here, is for every person in each group, how much they differed from their group mean. So this gives you, in a sense, a measure of just the homogeneity of variance assumption. Are the groups about equal in their variance? Are the times to campus about as spread if I go on Genesee versus I go on Gilman? We'll talk more about diagnostics for ANOVAs later on, but for now that's a nice quick plot that gets printed out and gives you some indication of what that spread is. Now you'll notice in this output we don't actually have any plot of the means like we did nicely when we did it in fit y by x. Now where it hides it is actually under this, well, it was above this leverage plot section here, which we minimized, this route dropdown. And this is actually going to be the place you'll find all the really specific information about your factor. The rest of the analysis here is really about the overall analysis of variance, the omnibus test, whether there is some evidence for some difference somewhere. But once we start looking into a specific factor, we have to go to that factor section. So in fit least squares or in this fit model section, you're going to find it here. And if we have multiple factors, you're going to have multiple sections like this. So if we were to put time into this model, we'd also have a section for time, and we'd have a section for the interaction if we're modeling it. So let's go to the route dropdown. And probably the most important thing, or the thing you'll want to see first, is just the plot of your means. So that's under the LS means plot, which is just called your least squares means. So if you request that, you actually get sort of a plot that you might be used to seeing. It's just our plot with time in seconds as the y, and our actual groups, or the conditions within the factor, on the x-axis. And so just like we saw before, this gives you an indication of really where the groups are, and probably gives you a hint about which groups are differing from which other groups. So you can see right away, if we were to just interpret this visually, La Jolla Village Drive is really the slowest route. It's taking on average, it looks like about 80 seconds more than the other groups down here. And Nobel maybe is a little bit slower, at least numerically. But the question that we always have is, do we have evidence that this is true in the population? I mean, just because we have a numerical difference in our sample doesn't mean that we have any evidence in the population, or over repeated samples, if we were to do it again, that we'd actually get this difference. Okay, so this actually is probably a good time to talk about these paired comparisons, or investigating whether certain means differ from other means, right? Which is going to be important, especially in experiments we do. We don't just want to know that there's a difference. We want to know who's differing from whom, or which groups or which manipulations are having an effect against which other ones. And to get those, we actually have a couple options. So if you go to the dropdown, again, you have actually 3 different ways to do these post hoc, or these planned comparisons, to compare a mean against a specific other mean. Those options are contrasts, which we'll talk about last actually, this least squares students t, and this least squares Tukey. HSD stands for honestly significantly different. And this is going to be our alpha corrected, or most conservative of all the tests we can run. I'll talk a little bit about what that is when we get to it. But go ahead and select the least squares mean students t. And what this is going to do for us, and I'll discuss what the output looks like. But what this is essentially doing for us, not essentially, what it is doing for us, is producing a student's t-test, so an actual, like that independent samples t-test that we introduced last quarter. It's doing that for every pair of means. So for, in this case, it's going to be Genesee versus Gilman, La Jolla Village Drive, and Nobel, Gilman versus La Jolla Village Drive and Nobel, and then La Jolla Village Drive versus Nobel. So it's producing all of those tests for us with an uncorrected alpha. So it's just as if we had no other tests being run, it's just doing those independent t-tests. So comparing each group to each other group. And what it's producing for us is this output, and I'll talk about why it looks like this, but it's producing really all the results for you as if you were to run these t-tests by hand, or if you were to do them individually. And this sort of crosstabs report is just a quick way for it to display a lot of information all at once, and I'll step you through what that looks like. At the top here, we have just each group, and on the left-hand side, we also have each group. And so the intersection of any of these two is the information that has to do with that comparison. So for example, if we wanted to see if Genesee was faster or slower than Gilman, we would look for that intersection, so right here. And notice that these are mirrored, of course, because Gilman versus Genesee is the same as Genesee versus Gilman. And what it's listing for you here are 4 numbers, and those 4 numbers correspond to these 4 numbers here, or these 4 pieces of information. So the first is the mean difference, so the mean for the row variable minus the mean for the column. So if I look here, this is Genesee minus Gilman, so this is telling me that Gilman is 2.7 seconds slower. Is that right? Yes, 2.7 seconds slower. It's giving you the standard error of the difference, and then it's going to print out for you the confidence interval. So, where we think this mean is in the population. And notice that anything that's in black here is not statistically significant. So notice that the confidence interval here contains 0. So our best guess of the difference between Genesee and Gilman in seconds is anywhere from 44 seconds faster on Gilman to 38 seconds faster on Genesee. Right? So we really have no evidence that in the population either of those would be different. Essentially, for me, that would mean I could take either of those routes and I shouldn't expect one to be on average faster. But if we compare Genesee to La Jolla Village Drive, on the other hand, you can see that La Jolla Village Drive is 82 seconds slower on average, right? And this confidence interval doesn't contain 0. That is, we think it could be at most 124 seconds slower to take La Jolla Village Drive, or as little as 40 seconds slower. But it's still slower, right? So I shouldn't take La Jolla Village Drive. And so this is a quick way to see it. Anything marked in red is a comparison that is statistically significantly different at an uncorrected alpha of 0.05. But this sort of grid way of looking at it is actually kind of slow if you want to get a sense of where all the means are. And a quick way that they've come up with displaying this is this ordered differences report, or this connected levels report. I think this is a technique Tukey came up with. He was really fond of coming up with different ways of visualizing things. But what this does, which is kind of neat, is that any letter or any groups that aren't connected by the same letter are statistically significantly different by whatever criterion you select. So for example, La Jolla Village Drive has the letter A, and all the rest of these have the letter B. So what that tells us really quickly is that La Jolla Village Drive is statistically significantly different from any of these by the fact that it doesn't have an A, or none of the other ones have an A in it, and that all of these are actually the same statistically. That is, we don't have any evidence that these routes differ at all from each other. And what you'll see sometimes, and we'll see it later, is that certain groups will have, for example, an A and a B. So imagine Nobel here also had an A on it. What that would indicate is that La Jolla Village Drive is not different from Nobel, but is different from, let's say, Gilman or Genesee. And that Nobel is not different from these ones either. So there can be indeterminate groups, groups that are stuck between different means. So this connecting lines or this connecting letters report is actually a quick way, especially if you have lots of groups, for you to see quickly which things are different. So essentially, the upshot of this would be I can take Nobel, Gilman, or Genesee and expect on average to take about as long, but I shouldn't take La Jolla Village Drive, right? That's going to be the slowest. One more thing about this, if you want to get all the actual output, so all the information, the t-test, the t-value, the p-values, all that, you can go to the drop-down and actually request detailed comparisons. And what that'll produce is for every single comparison, it'll plot out essentially the t-test that you would produce. It'll give you the difference, the standard error, t-ratio, degrees of freedom, and your p-values. So it'll produce for each one of these. And what you're looking at here is actually the sampling distribution under the mean difference. And so anytime that the distribution is shaded less than 0.05, or a proportion less than 0.05 is shaded, that's essentially when it's going to be called statistically significant. So this is just a way to get all those comparisons really quickly and for it to produce them really with no work for you. Now, one thing I'll mention too is that these analyses capitalize on the fact that you have a lot of observations and you have a lot of information about the variance that a single group doesn't actually have. Notice that the degrees of freedom for any of these is 36, right? If you were to actually subsample your groups, so actually just look at Gilman and Genesee, we would actually only have 20 observations, right? So we'd have 19 degrees of freedom for the variance, and we'd actually have a less precise estimate of the variance. So by doing the t-test in this way, by using the pooled within-cell error as your estimate of the population variance, you're actually getting sort of a benefit of those other groups being there, even though you're not really considering them in that mean comparison. So notice that in this case, Gilman versus Genesee, we're really ignoring the means from all the other groups, but we're using their estimates of variance. And notice that that makes a critical assumption, which the ANOVA already does, which is that the variance in each group is estimating the same thing. That is, that the population variances are all equal. So if they're not, if you have some evidence or some reason to think that, let's say Gilman is hugely variable and Genesee isn't, then using that pooled within-cell error from all the groups is actually inappropriate. So we can talk later on about why you would want to subsample or do partitioned ANOVAs to actually do these tests separately. But yeah, Tom.
And so that's why the standard error difference is the same in all the
Yep, in all the groups.
It wouldn't actually be if you just looked at these two piles.
Exactly, yeah. So this is capitalizing off the fact that you have lots of information. But yes, it can certainly be inappropriate if you have one group that's hugely variable, right? And you're doing that comparison with essentially what would be a reduced standard error. Okay, so these tests, again, we just ran 1, 2, 3, 4, 5, 6, 7 separate tests. Now these aren't totally independent tests, of course, they're using the same means in certain comparisons. But imagine that they're totally independent. Let's say they're totally independent tests that we're running. And we ran 7 of them, right? And let's say each of them was done, which they were at alpha equals 0.05. So that is, they're given a 5% chance, or we're going to reject if we get a mean that's different at less than a rate that we'd expect by 5% of the time. Then we're actually really inflating our type 1 error rate across all of the tests, right? We're giving ourselves multiple chances to get an outcome that we want to be low. It's like, for example, I say, roll 2 die, and I'm going to reject the null if you get 2, right? So if you get a 1 and a 1. But what if I let you roll the dice 7 times, right? The likelihood you're going to get that is going to be higher than what it would be if you just do it once. So alpha correction is something that we haven't really talked too much about, but it's kind of critical when you have lots of comparisons. We actually have to reduce or make stricter the criterion we use to reject the null hypotheses, or the null hypothesis in each of these tests, to really be fair to our alpha, right? Let me put it this way. Let's say you had a factor with 50 levels, right? And you do every single comparison you can. You're going to get a lot of results that are statistically significant just by chance. You're going to get way more than 5% of them that's statistically significant by chance because you have so many opportunities to find a difference. So to correct for this, or to actually be honest about it, the easiest way is just running this least squares means Tukey HSD. So again, this is honestly significantly different. And what the HSD is going to do is scale your alpha. That is, it's going to actually set your alpha level so that across all the comparisons you just ran, the chance of getting 1 is only 5%. So notice that before, we set each individual comparison to have a 5% chance of getting a statistically significant result by chance alone. But in this case, in the Tukey, over all of the comparisons we can make, so overall 7 of them, we're now keeping that alpha rate at 0.05. So think of it this way. If I were to redo this experiment and redo this Tukey HSD, I should expect, if there actually is no difference, that each of the experiments I do should only get 1 statistically significant result 5% of the time, right? It shouldn't get 4 or 5 or 6 of them. I should keep it low. Now, one thing you should notice about this, and actually let me minimize or take off this connecting lines thing so you can see this. And let me do the same thing here. Oh, before I do that, notice that it gives you the same output format. We're still getting the mean differences in this grid here, and it's still going to give you these connecting letters reports. But notice, let me take the crosstabs off. Notice in these 2 different analyses that different groups are now statistically significant from each other. that Nobel group actually is now indeterminate. We can't actually say that Nobel is slower than La Jolla Village Drive because they have the same letter. Basically, we don't have that statistical evidence anymore. Now, the reason it's doing this is because it's actually setting the criterion to reject the null at a lower value. It's keeping our alpha, or it's keeping the alpha for every single test low, so that over all the tests, the alpha is 0.05. So one thing that sort of sucks about this is if you have a lot of comparisons you want to do, doing a 2-key HSD is less powerful. But notice it keeps you a little more honest, right? So overall the test, you're not capitalizing on the fact that you just have a lot of comparisons you can run. And we'll talk more about this later, but alpha control is sort of a murky area. A lot of people don't do it at all. They just will run an experiment and do t-tests on everything. And in some cases that's actually fine, especially if you have a priori predictions about which groups should be different from each other. You're not really capitalizing on chance. You're just running an experiment and testing those specific things. But let's say I ran this experiment and I had no idea which means should be different from which other means, and I just sort of want to know across all of them, which ones I think might be different from each other. Then really I have no before the fact idea which means I'm going to test against which others, so I should be running something like a 2-key. I should be controlling for my overall alpha because I don't want to capitalize on chance. I don't want to say something is different when it really isn't, right? And the whole idea of running a statistical test is to make sure you don't say something is different when it isn't. So it seems almost silly to run an experiment and not control alpha if what you're doing the whole statistical enterprise for is to make sure you don't go out and say something is different when it isn't. So okay, we'll talk more about that later, and it does get, like I said, murky because if you have planned comparisons, a lot of statisticians will say don't correct your alpha because if you're planning to compare, let's say La Jolla Village Drive and Nobel, if you're planning that before the fact, you're going to make that comparison, then you're not really capitalizing on chance because you have a bunch of other groups in there. You're going to make that comparison. But really, if you're doing exploratory data analysis, that's the case when most people would say you really need to have some manner of alpha correction, something that actually controls your overall experiment-wise error rate. Okay, so 2-key and students T, those are the two ways we're doing these pairwise comparisons, that is every mean versus every other mean. Now, in chapter 4, I think it was, they introduced Bonferroni corrections. Now, Bonferroni corrections are, again, I don't know why he gets his own name for this, but it's this idea of just taking your alpha level and dividing it by the number of comparisons you're doing. So for example, if we're doing 3 tests, we're comparing 3 means, then we should just take alpha and divide it by 3, right? Because then we split our alpha rate across those 3 comparisons. And now you can actually do this if, for example, in this set of means we could compare, let's say we just don't care about a lot of them. All we really care about is whether La Jolla Village Drive differs from these other groups. Let's say before the fact, that was the only thing I was gonna test. Then this 2-keys comparison is actually overcorrecting our alpha. It's basically allowing us to look at every difference, right? It's correcting our alpha for all 7 comparisons. But let's say we just wanted to correct for 3. So what we can actually do, and let me take off these things. I'll just remove students T, remove this. What I can do is hold down Shift, go back to route, and do this students T test. And I could actually take my alpha and divide it by 3 and give that to JMP, and that's what it's going to run this test at for me. So if I just take 0.05 divided by 3, 0.0166, 0.0166. And so that's my corrected alpha for just 3 comparisons. And if I know which 3 I'm going to make, then I could actually go ahead and see if they're different. So La Jolla Village Drive now versus these things, I can say, well, it is different from Genesee and Gilman, but we really don't have evidence it's different from Nobel. So it's licensing me to make certain comparisons, but not others. We'll talk a lot more about alpha control. I just want to introduce you to the concept. But again, JMP gives you the ability to do this without having to do any work really on your own. You're not going to have to look up values and do these things. You can either use 2-keys or these Bonferroni corrections. Yeah, Joe?
So doing an alpha correction with the students T or doing the 2-key HSD, are they basically doing the same thing?
Sort of. So 2-keys goes about it in a different way. It uses a range statistic. It's just computationally it's different. Doing a student's T with a Bonferroni correction is literally doing just a student's T test, but making your criterion stricter for each of those individual tests. And actually, if you, let's say, for example, wanted to correct for all 7 comparisons, right? Because technically, if if we're running the 2 keys, we're probably interested in every comparison against every other, or every group against every other group. So if I do that, let's say 2 keys HSD, it's corrected for me. Let's say now I want to do the student's t-test with the Bonferroni correction. Let me go back and actually do it with shift. If I wanted to split alpha 7 ways, that would be 0.05 divided by 7 now. So 0.0071, 0.0071. So I can correct it that way, and it didn't make a difference in this case. But that actually makes our tests even more conservative than it needs to be. So what happens with Bonferroni correcting is after a certain point, 2 keys or these other methods like Dunnit or Chiffet's, they actually correct in a more powerful way. So unfortunately with Bonferroni's or doing this many comparisons, it's making the test really, really strict. And actually you can see, look at our t multiple here. Remember the t multiple is essentially what your criterion is, right? It's how much evidence you require before you call something statistically significant. And in this case, it's 2.85. And if you go back to the 2 keys, Q is essentially that. It's the range statistic, and it's 2.69. So the fact that that's lower actually is telling us that for this multiple comparison correction, 2 keys is a more efficient method. It's not overcorrecting. It's actually correcting in a less strict way. 2 keys will definitely keep your overall alpha at 0.05, but in this case, student's t is overcorrecting by using the Bonferroni correction. There's a whole chapter on this too. I don't want to, hope I'm not confusing the issue too much, but yeah, the methods definitely do differ. They're not doing the same thing. Yeah. Emily? Maybe. Yeah, well, oh yeah, yeah. Oh, no. It's actually perfect for this case. Yeah, Bonferroni's is really assuming independent comparisons, yeah. Because it's based off of Boole's inequality. And it's doing some, yeah, it's not actually a problem. It'll just be overly conservative if they're dependent, yeah. Okay, so really at this point I just want to introduce you to how you can get these paired tests, so how you compare one mean to another mean. And that's a quick way to get all of them, but a way to be really specific about things, especially if you know what you want to test, is to use contrasts. So if we go back to this drop-down, we haven't talked about what a contrast really is yet, but you can think about a contrast as just a specific comparison, and you use numbers to denote which groups get compared to which other groups. So when I requested the contrast, notice it gave me this contrast specification section. And what we can do is using these pluses and minuses denote which groups we want to compare to which other groups. So for example, a simple one might be La Jolla Village Drive, let's say, versus Gilman. And the way I can do that is just give a plus to La Jolla Village Drive and give a minus to Gilman. And if I do that and hit done, it's going to actually compute for me the test there. So it'll give me the t-test. It's going to do it as an F, just to be general. And it'll give me the p-value for that test. Now this is identical to the t-test that I just performed in the student's t. It's just doing it using a contrast. Now what's powerful about this is, let's say I want to compare something a little more complicated. So let me pull up contrast again, put this up higher. And let's say I'm not really interested in La Jolla Village Drive versus one mean. I'm actually interested in La Jolla Village Drive versus the average of all the others. Let's say there's some reason for that. For example, actually let me do it this way. Let's do Gilman versus the rest of these, because perhaps Gilman actually has an earlier exit. Maybe I think there's something special about taking Gilman versus all the others. So I want to compare the average of all the other groups versus just one mean. So I could take Gilman, give it a plus, and then I just hit minus on all these other ones. And notice what it's going to do is now Gilman gets this positive 1, and Genesee and La Jolla Village Drive and Nobel get a negative third. Now, there's a reason why the numbers are the way they are. Contrasts have to add up to 0, and they need to have an absolute value that adds up to 2. The latter is not really a requirement, but it's just the way that things are typically done. So JMP is enforcing that rule. But essentially what this is doing is it's taking a third of each of these means to make one mean, and then it's using Gilman as just its own mean. These are essentially multiples of a linear combination. So it's 1 times the mean of Gilman versus 0.3 times the mean for Genesee plus 0.3 times the mean of La Jolla Village Drive plus 0.3 times the mean of Nobel, which is just to say it's an average of those 3 versus this 1. And that'll become more clear as we talk about contrast more. But if I hit done here, this actual contrast, this comparison it's producing for me here, this is actually the test of Gilman versus the average of all the others. Now, in this sense, it's sort of silly to do it this way because there's nothing really special about those three. But there might be times in an experiment where you have, let's say, two conditions that share something in common and you want to see if they differ from another. For example, two conditions that deal with people, for example, and one that deals with an abstract entity or something. And you, for whatever reason, don't have your factor laid out that way as that versus that. You can just do the contrast specifically in here and get that comparison. And Mark will talk about this more later, but within factorial designs, all factorial designs are really just one-way designs with contrasts that pick up certain things like interaction terms or marginal effects of certain groups. So contrasts, as you'll come to see, are really your friend. You can run pretty much any analysis you want using a contrast, and you can do it rather quickly in JMP, which is really powerful. SPSS definitely lets you run contrasts as well. To do custom ones like we just did, you have to use syntax in SPSS. SPSS by default does polynomial contrast and some other types, but and we can talk about those later. But JMP makes it really simple, which is nice to do these things. Okay, hopefully that was sort of clear. Now, we were doing this all under fit model. I want you to notice that if you were using fit y by x, you could actually get to the same mean comparisons. So if we go to that drop down, you can see under compare means, you actually still have the options of each pair doing the student's t-test. You have also the Tukey, so this is the protected overall error rate. So Sue's test, or I can never do that, but this actually will take whatever the best group is, the highest mean, and compare it to the others. This sometimes gets used in medical studies where you don't really know which drug is going to work best, but you know one of them is going to be best, and you want to compare that to the rest of the drugs. It may seem strange that there's actually a test that does alpha correction for that, but if you think about it, if you have no idea which group is going to be best, you're capitalizing on chance by just letting it be any of them, and then comparing to it. So this actually makes those corrections. And then Dunnett's test is essentially just comparing all the groups to a control. So if you have a control group or some control condition and you want to compare it against that, but still control your alpha, notice that you're not running every comparison, you're just running those groups against one group, just like we did when we corrected for just comparing against La Jolla Village Drive, right? So that's what a Dunnett's test is. All of these are a little bit repetitive if you're just going to correct using Bonferroni or Tukey, but we can come back to those a little bit later. But notice you can do all the same things really in these two platforms, except for contrast. You can't do in fit y by x. But pretty much at this level, if we're just running a one-way analysis, we can do it in either. Now the place where it's going to be important to use the fit model is when we actually get into factorial designs. So when we don't have just one factor, we actually want to consider the effect of two factors simultaneously, because we presumably want to see what that interaction is. Everyone loves interactions. So let's actually do that. So going back to our data set, remember that we have this time factor, right? So this time variable. Now we could just look at the effect of time individually. So we could run this analysis. You don't have to do this, but I'll do it real quick. Just to see if time actually has an effect on the time to campus here. So you can see if we were just running it alone, first off, the effect of time is non-statistically significant. So we don't really have evidence that anything is happening with time of day. Looks to be about the same. Numerically, though, 8 a.m. took a little bit longer in our sample than the other groups. But right, we don't have any evidence that there's really anything we should expect about the time of day. But by collecting these data as we did, we actually get the benefit of looking at those two factors at the same time and that interaction. So to set it up, we have to do something we haven't done before, which is using this cross feature. Because what we're doing when we think about making the models, we have an effect of, I'll do it one way, then I'll show you a faster way to do it. But we have an effective route, so if you just add that into a model effect. You also have an effective time, but now you have this combined effect, so the interaction between these two. So if you select both of them and hit cross, it'll create this thing that's time by route. So essentially it's looking at the interaction of these two, and that's how you're going to specify that model. Because what you're doing is you want to look at basically the compound effect. Is there something special about being in a condition within one factor? So something special about, let's say, 8 a.m. In a certain route, or something special about the time of day for a particular route. And when we actually look at the plots, it'll become a little more clear. So that's one way you can specify the model. This is just called a full factorial. This has both marginal effects, so route and time, and then the interaction term. So there's a way we can do this quickly if you just delete those two. If we take time and route, select them up here, you can actually click on macro and select full factorial. And what this will do is actually just add those model effects for you, plus that interaction term. So it actually puts everything in there for you. Now this is especially useful. Let's say if we had 3 variables, this is going to be nonsense for us, but let's say day was also a different factor, and we wanted to make the factorial. Notice that we'd have to, if we were to do it manually, do all of this. We'd actually have to put in the day, time, and route marginal effects, put in the day by time interaction, the day by route interaction, the time by route interaction, and the day by time by route interaction. So we wouldn't want to do that manually, so that's what that full factorial is. But that's nonsense, so let's go back to this. Okay, so once you have that set up, go ahead and hit run. You'll notice that everything looks fairly similar. We have more leverage plots, and we have some more stuff here. But the first thing we're going to look at, though, is this analysis of variance, right? Is there something happening? Do we think there's something special about some group? Or is there any reason to think that groups are not coming from the same population? And we still have that evidence. Effect tests, probably the next place that I would look. What's our effects of each factor, right? Is there something overall that's happening? So time of day, notice now, if we look at it, we actually do have some statistically significant effect here. Unlike before, when we actually didn't find an effect of time, now in the factorial, we do see something. And this actually happens quite commonly because notice when we just looked at the effect of time and looked at the effect on the duration of the drive, all that information about route, all the variance those means soaked up by having the differences known, got soaked into within cell error. Basically, the model had no idea that the routes were differing, and so it just looked like error to the model. But by having it in the factorial, the model can say, I don't want to anthropomorphize things, but the model can say, I know what the effective route is, and these means are differing, and then I can get a more precise estimate of sort of the within cell error. So anyway, we still have an effective route here, we have an effective time, and we have this time by route interaction. And for those of you who haven't thought about interactions much, what this essentially is saying is that there's something specific about a certain, let me say this right and not nonsense, that the effect of one factor depends on the level of the other factor. So the effect of time, for example, depends on which route you're in. So maybe in certain routes, the time of day doesn't matter at all, but for certain routes it does. Or said differently, the effect of route depends on the time of day. So for example, at certain times of day, maybe the routes don't differ at all, but for a certain time of day they do. So one level of, or the effect of one factor can only be described within the levels of the other factor. And we'll get a handle on what that looks like as we look at the means. But again, this is our effect test, so this is where you look for just the marginal effects, or main effects as people like to say. That's really marginal effects, the effects at the margin of your sheets if you were to do these by hand. But what we'd probably like to know really is what the effects are, right? What the means look like so we can get a handle on what's going on. So notice that we have these 3 sections now. We don't just have a route factor effect. We actually have the time, the route, and then the time by route, that interaction. Let's get the plots for each of these. So let's do least squares means plot for time. And notice as before, we have the same mean differences. So 8 o'clock is actually slower than the rest of these times. But the error bars, if you remember, are now a lot smaller than they were before. Has to do with the precision with which we've now been able to estimate these means. Let's do the same for route. We've seen this plot before, but we might as well pull it up. So again, this is the effect of our route here, and the Hoya Village Drive is still slower. But the interesting new thing is going to be over here with this time by route. And what this is going to produce for us is essentially the factorial plot. So broken up into every cell mean, so every combination of route and time, it's going to plot for us. So let's go least squares mean plot here. And let's drag this out so we can see what's going on. And what you may notice now is that, what you may notice now is this interaction is sort of clearly happening in one place right here. So if we, again, think of what the definition of interaction is that the effect of one factor depends on the level of the other. The effect of time of day doesn't seem to do much for Genesee, doesn't seem to do much for Gilman, but seems to make a big difference for La Jolla Village Drive, right? And then back down here doesn't seem to make much of a difference for Nobel. And this is actually based on my own experience. If you try to go on La Jolla Village Drive at 8 a.m., it's just dead stopped because people can't drive and they don't know how to use traffic lights. So it's just totally stopped, and so it's really slow. So essentially, just looking at it, we can see where that interaction is really coming from, right? Now another way to plot this would be, of course, to have time of day on the x-axis. And this is just a trick you need to know because I don't think it's documented anywhere. But let's take least squares means plot off. If you hold down the shift key and then request it again, it'll switch the axes for us. So now you can see just a different way, and some people find this more helpful to visualize. But now we're looking at time of day on the x-axis and separate lines as the routes. So you can see again, at 9 o'clock and at 8:30, these means are essentially close together. But at 8 o'clock, one of these means is very different, right? So it's much higher. But of course, right now we haven't tested anything. We've just looked at the means, right? We don't actually know whether these things are statistically significantly different. Now, we could go about, and I'll do it for you, but you don't have to. We could go about requesting every comparison using student's T. That looks messy and kind of gnarly. So you could do it that way, and look at it in here. Quickly, you can actually get a great idea of what's going on if you look at this connecting letters report. And you can see that this is a really nice way of looking at lots of mean comparisons. So we can see that 8 o'clock La Jolla Village Drive is different and slower than everyone else, right? And then Genesee is faster than these people, and then the rest of these are just sort of indeterminate. They're in the middle. But this is sort of messy and a lot of comparisons. And if we didn't have any idea of what we were testing, this would capitalize hugely on chance, right? The number of comparisons we're making here. So if we wanted to be a little more specific with ourselves, that's weirdly up there. Let me just get rid of that altogether. Let's say we just want to run a contrast. We just want to know specifically, is this point different from, let's say, the average of these three? Because these ones look about the same, so let's compare 8 o'clock La Jolla Village Drive to the average of everyone else at 8 o'clock. We can actually do that with a contrast. I don't know what you are, so no. So we get our contrast panel here. And what I said before I wanted to test was, let's say 8 o'clock La Jolla Village Drive, I'm going to give a plus, compared to everyone else at 8 o'clock. Is it different than the average of the rest of them? And so we just hit minus signs. It's going to scale it, so it keeps the sum at 0 and the absolute value of the sum at 2. And we actually get this statistical test. So our F ratio is massive and our p-value is small, so we definitely have evidence that that route is slower than the rest of them, than the average of the rest of them. And we could do the comparisons with each of the other ones or with the average. Sometimes it makes more sense to do certain things, but definitely it gives you the ability to make these comparisons quickly. Now another way, again because it was so messy to look at all the comparisons, is something called testing slices. So I'm going to actually get rid of that contrast here. And under the drop-down, only under the drop-down for the interaction panel, you have this test slices option. And this is going to do something interesting. Notice that at every time of day, we can consider this as a slice. So really at 8 o'clock, we have an ANOVA, essentially, another ANOVA we can think about comparing whether or determining whether it makes sense to think about these means as coming from the same population. We have a slice at 8:30 when we can think about, is it reasonable to think that those means are coming from the same population? And the same thing at 9. So we think about the slices in terms of the time of day. You could also think of slices in terms of the route. So for Nobel, do we think it's reasonable to think that the times are all coming from the same population? And the same for the rest of these, right? So these are essentially sub-design analyses of variance, right? It's, do we think it makes sense to think about means within a certain slice as coming from the same population? And it can do all these analyses for us just all in one fell swoop here. So for slice time of 8, this test is essentially, do we think it's reasonable to think the routes are all the same at 8 o'clock? And we find certainly not, right? There's no reason to think that they're the same at 8 o'clock. Our p-value is very, very small. At 8:30, we haven't really exceeded our standard of evidence if it's 0.05. So we say we really don't have evidence at this point that at 8:30 things are really differing from each other. and the same is true at 9 o'clock. We really don't have evidence that groups are differing from each other at this time. And if we consider the routes now as the slice, we can say, does time of day make an effect for Genesee? Doesn't look like it does. We don't have evidence that it does. Does it make a difference for Gilman? Doesn't seem like it does. Does it make an effect for La Jolla Village Drive? Yep. And does it for Nobel? Doesn't seem like it does. So this gives us these tests that are actually rather annoying to set up if you were to do it on your own. If you go under test detail, it'll actually show you the contrasts you have to set up. We'll talk about this too. These are compound contrasts. So you actually have 2 degree of freedom, not 1 degree of freedom contrasts. I won't get into that now, but these are the functions it sets up. If you look up under, let's say, time of day, you'll see that it actually is a 3 degree of freedom contrast. Not that that makes any sense to you at this point, but it's great that JMP does this for you, is the point I'm trying to draw here. So it actually is doing these essentially sub-design ANOVAs, looking at the effect at one slice of the other factor. Okay, so as far as factorial stuff goes, nothing really has changed, right? Setting up the model was the only thing we had to do a little bit differently, and we get this extra panel where we get to look at the sort of combined effect of both factors. We get that interaction effect test. Now for our particular analysis here, it was really clear right where the interaction was. We had that one group that was very different. Sometimes it won't be that clear, in which case this thing called the profiler is actually really useful. So under the top, under factor profiling, there's a section called profiler, which we've seen before, and I'm just going to expand this out. And let me make this up here. And so what profiler does is lets you really dial in whatever level of each factor you want and look at how it affects the sort of response function for the other factor. So at 8 o'clock, notice the effect of route looks like this. But at 8:30, the effect of route looks much more flat. And at 9 o'clock, the effect looks even more flat. And so you can actually switch back and forth, and you get a real quick sense of really what's differing between these things, right? Where that interaction is lying. And you could do it from either really perspective. We can look at the effect for Genesee, not much effective time. At Gilman, very little effective time. La Jolla Village Drive, a big effective time. And then at Nobel, no real effective time. All right, so it lets you really grasp or understand what's going on in your data. When you get into 3 and 4 and 5-way interactions, this gets to be, well, after a 3-way interaction, it's sort of insane to try to interpret anyway. But at least for visualizing your data, the profiler gets to be really, really useful. What's really interesting, too, is when you start getting into more complex models, Anakovas or complete block designs, things like this, where you actually may have quantitative variables, too, in these models. You can actually look at the response on the quantitative factor for different levels. And this is something that's really hard to visualize normally. But imagine we're looking at, let's say, a regression function over here, not an analysis of variance. You could actually see what the regression function looked like for different levels of this factor, which is a really neat thing to be able to visualize. And it's very difficult in most other programs. So this profiler is really useful. And it's also a real good quick place if you need a table that has just the means for each of your cells. You can actually go to the drop-down and actually say output grid table. And it's just a really quick way if you need just a data set that has your time, your route, and your time in seconds. And it's just a quick way, and it'll break it down for every cell in your design. Not that you can't get this other ways, it's just very quick if you've already run the analysis here. If you want to get really fancy, especially if you're doing quality control stuff, you can set in desirability functions and lots of other sort of optimization things, which we won't get into. And if you really want to get fancy, you can run the simulator, where you can actually simulate data off your existing data using your mean structure, and you can have it treat things as random effects or expression effects. You can do all sorts of really interesting things. If you need to create data, for example, to sort of fit models to or try out different things. So this prediction profiler does a lot of cool stuff. But for our purposes right now, we're really just looking to see what our interaction looks like, because that's usually the most difficult thing to sort of grasp, especially with more complicated designs. Okay, now the last thing I want to mention is these parameter estimates. So now they've gotten extremely complicated for us because we have this interactions, or the interaction term in there. But again, these parameter estimates are, well, let me go back to a simpler model because this is going to be gnarly. let's just keep route in there. So remember when Mark was talking about the different ways to parameterize a model. We have a cell means version, which is essentially modeling the parameters as just the cell means without a grand mean, which is very interpretable, right? So the parameters you estimate for the model are just the means of your groups. But there's also this factor-coded model, right, which is to model essentially the effect of being in a group as some grand mean plus some effect, so some treatment effect for that group. And that's essentially what we have here. We have some grand mean, 628 seconds, and the effect of taking Genesee is for my route to be 29 seconds faster. The effect of taking Gilman is 26 seconds faster. The effect of La Jolla Village Drive, 53 seconds slower. Right? But notice that we're missing something here, right? We don't have Nobel. And that's essentially because when we do the factor coding, remember we had to impose that restriction, the sum of all the taus equals 0. So that last group is actually redundant. We don't actually model a parameter for it. It's just we know it to be the sum of these separate taus. If you want to see it, you can actually go under estimates and get expanded estimates. And it'll print it out for you down here. Scroll up here. And notice that now we actually have this effect of Nobel. And if you're playing the home game, you can actually add up all these, and you'll see that they will sum to 2.925. But I make mention of this because it's really easy to expand this little parameter estimate section and think that these are effect tests or effects of things. But notice that these p-values here are really telling you whether these particular groups or these particular taus differ from 0. Right? So is this group different from the grand mean is what that p-value is telling you. And for most of our experiments, that's probably not a very useful thing because the grand mean in your experiment is completely dependent on what groups you observed or what your manipulations were. So these parameter estimates, the reason why it's hidden by default in designed experiments or in analysis of variance, which is usually for designed experiments, is because they're just not values you typically need. But notice that these are essentially the taus. This is tau 1, tau 2, tau 3, and tau 4, which is implied, is just the sum of these different taus. So if you do need the parameters for the model, they're here, but in analysis of variance, you just don't do it. It's just not something that is commonly done. Now, one of the homeworks, you're actually going to create columns that correspond to this factor level codings. So if you remember in the book under this section, there essentially are ways to create a data set such that you can run regression type analyses on your data set, and it'll produce essentially the same parameter estimates for you. And so if you want to, and I think one of the homeworks it's asked you to do this, you actually create, in this case, 3 new columns that'll correspond to these sort of factor codings. And what you'll be able to do is run the analysis and get the exact same parameter estimates. So if you were stuck on a desert island and you only had a regression program and you had to do an analysis of variance, you could do it, right? But that's sort of bizarre. So again, these parameter estimates, typically not useful at all for us, but just notice, I want you to know what they are so you don't come to them later and say, oh, that's totally my effect test, and it's not. But if you have to know whether this group is different from the average of all of them, this is a place you can look, right? Also, if you need to know whether your average, your grand mean, is different from 0, which sometimes is the case in different scores. For example, let's say all your groups are based on different scores, so a difference of 0 means something. This intercept test here, this p-value, this is testing whether that intercept, your grand mean, is different from 0. So that test actually is produced if you actually needed it. Not that you can't get it other places, but I'm just trying to think of reasons why you might look in this panel, but probably you never will for an analysis of variance. So we'll just minimize that again. Okay, so that's really all I think I was going to talk about for analysis of variance and JMP profile, blah, blah, blah. Yep. So in 2 weeks, we'll come back to some of this, and we'll talk a little bit more about contrast because we'll have learned enough to do some really interesting ones, so polynomial contrasts and interaction contrasts. But for now, just know they're there, and for the homework, I think you have all the stuff you really need to actually produce the outputs. Starting with homework 3, every question that uses JMP will have its own video, so you can just watch me solve the problem. And I have to redo them. I think for the first homework that I start doing them, they have no sound, which is super annoying. But I'll fix that. But so every homework answer is now demoed out, so you can watch how I do it. But if you have any questions about tonight, I can field them now. Otherwise, that's all I got. Okay.